So I was saying that, so welcome back to all of you. I was just going to show you the first couple of steps of the practical. The easiest way to get hold of the files is to clone the Git repository here. So you can do that on Archer, as I've just done. I'll do it one more time just to show you what I was talking about. So if I just made a directory, something like course 2, and then I clone the repository, and it's copying all of the files into the directory that I want to work with. So you'll see that the full structure is repeated here. The workbook that you want for this first practical on linear regression is in section 105. It's this file here. But you don't, but now that we've got it on Archer, the way that you'll access it is through the Jupyter interface. So remember to connect, you should put in this address here into your browser. And it will start this Jupyter Lab session. You can navigate, so you should see that all your files are here on the left-hand side. So this is all the files on Archer, because we're remotely connecting to Archer here. So this is all on Archer. Course 2 is the directory that I just created 1 minute ago. And in there, in section 105, I think it was this quick practical introduction to linear regression. And if I open it from here, it should open in a new tab here. So what we're going to do here is a sort of, this bit shows you some quick introduction to some linear regression things. And if you're not familiar with how these notebooks work, most of this is just a walkthrough, really. There's some little bits for you to try to have a go at yourself. I don't think the answers are in the repository yet, but I'll make sure that they're there after the course. So if you want to see how I tackled them, you can have a look there. But where these notebooks work, you can go through them cell at a time by pressing Shift Return, and it executes all the commands in each notebook cell. So you can just walk through and look at the commands that are there and check that you understand what is going on as you go through. So yeah, hopefully it's fairly self-explanatory. If you're having any problems, just let me know. Some of the challenges a bit further down. This is to get you to sort of get a little bit of practice of writing, converting equations to code, if you like, being able to work out yourself how you could calculate this cost function in Python. Even if you can't sort of fill in all the gaps yourself, hopefully you can see what's going on. So as I say, most of it is a kind of step through. But if you try something out, you don't really understand what's going on, and you have any questions, just let me know. Okay. So I think this new prax bit was just wherever whoever wrote this notebook saved the data. So wherever you've actually, if you've used the Git repository, you will already be in the right directory. So there is nothing to do here, because it says make sure you're in the folder where you save cats.csv. Cats.csv is in the repository in the same directory, so there should be nothing to do. You can just ignore that line. Okay, Gudrun, your session died. So you tried to open a node with a longer session than 20 minutes. Let me just have a check. Yeah, so yeah, I can't remember what the right reservation is. A workaround is just to use the front end. Then you won't need to connect to the back end. Yeah, the login node. You can do this in the login node. Sorry, I forgot that there was going to be a time limit on the compute node. Yeah, because it's going to be frustrating if you keep getting logged out. I'll check with my colleague what the right queue, the right quality of service should be, and I'll get back to you. But in the meantime, I suggest that you try the login node. Sorry about that.
I do have a question.
Yeah, okay.
So if I run the regression, do the linear regression, and I get this reg parameter variable, and then I get the coefficients and the interception point with reg.intercept, I get a point that is minus 0.35 something. Now above. Still slightly, yeah. So here this, but if I look at the graph, and maybe now I'm completely wrong, shouldn't the interception point be something around 6 point something?
Except that the x-axis here in this plot does not.
Oh, it shifted.
It's just
Okay, got it.
Continuing down.
Sorry.
Yeah.
Yes,
Sorry, it wasn't clear, but yeah, that's what's happened.
No, that was just me. Misinterpreted. Sorry.
No problem. Sam, sorry, when I started to answer your question, I was indeed muted. So I was saying, the problem with I've just realized I hadn't I had forgotten that it's got this download step in here. I presume you're running on the back end. The back end nodes, the compute nodes, cannot see the internet, which is one of the complications of trying to do this kind of thing on a machine like Archer. To be honest, you only need Seaborn for this pair plot here, if I remember correctly. This one here. It's just a visualization library. Everything else should be installed. In fact, I wonder. So maybe Seaborn isn't there on Archer by default. I would recommend just ignore don't try to install it if you're on the back end and miss out the bits where it tries to use Seaborn to do a pair plot. Alternatively, you can go back and do it on the login node, which can see the internet, but yeah, it's probably not worth it just for those two diagrams. Sorry about that. I forgot that point. It also doesn't have access to scikit-learn. Do I try? So scikit-learn it shouldn't need to download. Do I do an install scikit-learn somewhere? Let me just check. That might work, John. Although I thought, unless it could be that I've just already had scikit-learn installed. I thought this was tested so that everything was installed. Wait a minute. So I thought all of scikit-learn was installed, but if it's not, I'm just going to see if one of my this was meant to be checked. Learn pandas. Okay, so pandas, scikit-learn, these should all be available, but let me just check. So Andrew, thanks for your suggestion. The people who are running on the back-end node can't see the internet because they're on the back end. So doing it inside a notebook, like you're trying to do with the exclamation mark, might not work. What you could, the pip install might work from the login node, and then it might be visible. Pandas appears for me by default if you've done module load cray Python. Okay, thanks, John. What about scikit-learn? Did that appear, or does that one not appear? Scikit-learn doesn't appear with cray Python. Sorry. Okay. So can you try on a login node this? And see if it puts it somewhere where the notebook can see it. So it would have to be on a login node. So if you So John, okay, you said module load create Python gives you pandas, but it doesn't give you sklearn. Okay, so yeah, the Python -m pip install scikit-learn on a login node, I think should work. That hasn't worked for you. You also restarted the server. That's what I was going to suggest next. I'm trying with Seaborn here because I've already got scikit-learn. So when you type, so rather than try to do it in the Jupyter Hub, when you just open Python as an Archer command line, like I've done it here, does import sklearn work there? Yes. So it works there, but it doesn't work in the notebook. So if I now go back to my notebook, I'll try the same thing with Seaborn. Sorry about this. I've just installed Seaborn. What can I try? I'll try another one. Going really slowly. What's it doing? It has worked. These are maybe things I've already got installed. I need something I've not got installed. It's maybe a bit of a big one, a bit overkill. That might be the workaround just now, Sam. I'm sorry about this. I'm just trying to recreate using a different library. Okay, a little note to everyone. You may have been listening to some of the conversations that have been going on. If you're having trouble, if you're trying to import scikit-learn or sklearn or any of these libraries and it's not importing, probably the easiest thing to do is to make sure you're on a login node, so not a compute node, a backend node, and then you issue the command Python -m pip install sklearn. So Sam, you managed to get it to work. I needed to re-log into the compute node, exit 0, then srun again. So it must be something in the environment that wasn't set, that gets set when you log in. I'm glad you managed to get to the bottom of it, but I don't know, I can't quite explain the order where it's picking things up. It'll be a path or something. I'm glad you managed to get it to work. It should work. It's just getting things done in the right order. So, I'm sorry, I thought I was working from a vanilla thing when I was testing it, but I must have already had scikit-learn loaded. Okay. So for everyone else, yeah, if you haven't got scikit-learn when you try to import it, so it's import sklearn, but if you're installing it, it's got its full name, which is scikit-learn.
Hey, can I ask a question? I've not used Seaborn before. Is it generally just a better plotting library?
It's generally just a better plotting library, yeah.
Okay.
It's yes, exactly. It's got a few other things, like it's got some data sets in it. So I think, I can't remember if one of these practicals uses I know this one just gets it from online, but Seaborn has some built-in sort of test data sets that you can use for visualization and to run things on. So I sometimes use it for that as well, but it's mostly visualization.
Cool, thank you.
Okay, a few little wrinkles there with that practical. Sorry, hope people have managed to make some progress with it. If anyone is struggling to get it, well, I'll try and update the repo so it's got everything in it. But the things with scikit-learn and so on, you could also try on your own laptop with the Anaconda distribution if that makes it easier. We are now at 2:10, so okay, thanks, John. You might be right. It is missing fig1.png, I can see that, so I will have to fix that. Okay, I'm going to move on to the next lecture just now. We can come back to the practical part a little bit later on. So we're going to have a quick look at some k-nearest neighbors classification now. So the first of our classification examples. Just load up the slides. Okay. So to go back to our tree of different topics, we're now going to stay in the supervised learning branch, but we're going to move on to classification. So trying to predict or identify specific classes that things fall into, rather than trying to predict a number, which we were doing with regression. So the problem overview here, the input to classification is one or more features. So features, things like the size of the house that we had last time round. Our features now can be either numerical or categorical. The output variable is a class or a category. So the classic example that you often see in a lot of machine learning texts and so on is this iris data set. So here's an iris, and the idea is you're meant to be able to detect whether this iris is a setosa or versicolor or virginica iris by looking at its features, namely the petal length, the sepal length, and I think there are two other features in the data set. So if we found a new iris and we noticed that it had a petal length of 1 and a sepal length of 5.5, so it would fall here, you could probably tell, looking at this training data, that we would want the algorithm to class this as a setosa, because in this case our classes are fairly easy to separate. So it's quite obvious, at least to the human eye, that another point here would probably fall into the red set. Similarly, if we had a petal length of 5.8 or something and 6.2 for the sepal length, we would probably say, okay, that one's a light blue, that's a virginica. If we had one that was here, it's maybe a little harder to classify. Should it be a green one? Should it be a cyan one, a light blue one? It's maybe harder for us as a human to detect, and it is in fact harder for a computer to detect as well. But the problem, this is the kind of problem we're trying to solve with classification, is given some example data, can we predict what class, what category the new data points fall into? So we're going to look at the first algorithm that we're going to use for this is a pretty simple one called k-nearest neighbors. So with k-nearest neighbors, the question becomes, so this is a sort of idealized diagram, like with the last picture that we had, the position in space here corresponds to the value of the features, and the color represents the class or the category. I meant to change this one to red and blue. Sorry, I do apologize for anyone who's red, green, colorblind. These points over here are red. The ones on this side are green. The question is, what class should this point fall into? And k-nearest neighbors says, okay, let's pick k equals 2, and we'll look at the two nearest neighbors to this point. Have I got this right? And if I pick k equals 2, well, let's pick k equals 3. Okay, that was easier to explain. If I pick k equals 3, this is what the diagram depicts. That means I look at this point, and this point, and I can see that I've got 2 greens and 1 red. So therefore, green wins, and I decide that this one must be should be green as well. You probably spotted the obvious problem here. Well, what if I picked k equals 6 instead of k equals 3? Now, if I looked at the 6 nearest points to this point, I would see that 4 of them were red and 2 of them were green. So I would pick red as my output class. So it's not without its problems, k nearest neighbors. Your answer can depend on k, but it's normally possible to find a value of k which makes a reasonable prediction for which class the point should fall into. This is one of these tricky cases that's sort of between the reds and the greens, which is why it's difficult to predict. if you picked one over here, it wouldn't really matter whether you chose k equals 3 or k equals 6. You'd probably find that it would be definitely red anyway. So there's two decisions to make when we're doing this kind of using this kind of algorithm. One is how we define similarity or closeness. So we just used the sort of our normal definition of Euclidean distance when we were looking at the distance between these points. But in general, in machine learning, one of the things, just like we could choose different values of our cost function, we can choose different distance metrics or similarity metrics, and they can lead to slightly different answers. And the other question is, how many neighbors should vote? So here, in this machine learning algorithm, we have a new kind of hyperparameter. We don't have a learning rate here. What we have is a value k that you have to decide on when you're doing your classification. So the general approach, though, is very similar to what we did in regression. So we have some kind of training set. We've got our hyperparameters. We choose our values of our hyperparameters somehow. We choose our definition of similarity. We put these into the algorithm along with the features of an unknown instance, and the model then categorizes that as a particular kind of iris. So, yeah. So Euclidean distance works well for real valued features. So Euclidean distance is just a normal kind of square on a hypotenuse type distance. You just add up the differences in each dimension. Sorry, you find the differences in each dimension, square it, then add them up and take the square root. Because we're doing this kind of distance thing, just like the example we had with the regression, for this to be meaningful, it's normally necessary to normalize your data or to scale your data. I mean, if we had something, features like age and salary here, for example, if you plug these into the distance algorithm, the salary effect would completely overwhelm the impact of age, because these values are so much bigger. So when we are doing these kind of machine learning algorithms to do classification, it's very common to normalize the data first. In other words, you sort of subtract the distance from the mean and divide it by the standard deviation, so that everything is, all the features are of a similar size and spread. Another thing that you should try to do, it's not always easy, but it's good to avoid highly correlated features. So we haven't really talked a lot about correlation here. In a longer course, I might have done that first. But the idea in correlation is that there's the same kind of information stored in more than one feature. So again, if you have many correlated features, they can unduly dominate the classification. So for real valued features, Euclidean distance works quite well. But here's some examples of some other distance functions you can use, because remember, we were saying these same kind of algorithms can be used whether you're classifying text or images or tabular data. So imagine if what you're trying to do is to look at two sets, and say one set contained sheep, cow, and hen, and another set contained the words cow, horse, and hen. So maybe you're trying to do document classification based on just the words that are in the document, for example. You're not interested in the order or anything like that, maybe, or the count of each number of words. You're doing a basic bag of words document classification, and you want to know how similar two documents are to one another. Then your input features are the sets of words. So, but you need a number out to do k nearest neighbors. So one way of getting a number is to calculate the Jacquard similarity. And what you do there is, first of all, you calculate the intersection between A and B. In this case, the intersection is how many words are in both sets. So cow is in both sets, hen is in both sets. So the intersection here is 2, and you divide it by the union of the two sets, which is the total number of elements in all the sets. So we have sheep, cow, hen, and horse. So that'd be 4. 2 divided by 4 gives you a value of 1/2. So you can see that if they had exactly the same things in common, this number would tend towards 1. If they had nothing in common, it would tend towards 0. So that satisfies the kind of thing that we want from a distance function. If they're similar, so similarity and distance are just kind of reciprocal of one another. Sometimes we talk about things being similar, in which case you want that to be a high number. Sometimes we talk about a distance, in which case you want it to be as close to 0 as possible. You can just flip those. You just do a reciprocal of a distance to get a similarity. Another one used often in text processing is something called cosine similarity. This is measure an angle between two vectors. So if you can imagine a vector going out from the center of your space to the point where your different instances, different rows that you're trying to compare, you'll end up with two vectors, two lines going from the central point out in different directions. The cosine similarity measures the angle between those two vectors. And in that case, it can go between 1, with them being identical, -1 if they're diametrically opposed, and it'll be 0 if they're completely independent of one another, so orthogonal. And that value, you can get that from this equation, taking the dot product and dividing by the product of the norms. And then again, so this is another thing that can be used to classify documents, for example. Quite often, to represent a document or a piece of text, you turn the whole text into a sparse vector with one number for each word in your vocabulary. So if this is your vocabulary, I love, I hate, delighted, broken, and not. This, in some cases, often a vocabulary will just have single words, but you can have multiple words like this. You would say, is I love in my string? Yes, so put a 1 here. Is I hate in my string? No, so you put a 0 here, and you build up your vector, and then you can compare these two vectors to see if they're pointing in roughly the same direction. So again, this is a way of taking data, taking 2 points of different kinds, sets or strings of text, and converting them into a number that you can use on an algorithm like k nearest neighbors. So there was a question, I think. How many dimensions do I have to deal? So you have a dimension for each. So in this case, for example, you would have a dimension for each word in your vocabulary. So that could be pretty high dimensional space. If you've got a dictionary with 100 words in that you're using as your vocabulary, you're working in a 100 dimensional space. That's fairly common for some of the natural language processing that uses this kind of technique. And again, so these algorithms work in any number of dimensions. The algorithms don't care. So k nearest neighbors, you could have as many directions as you want. Hard to visualize, but perfectly fine for the algorithm to calculate. And you can, have as many dimensions as you want and still be able to define which points are close and which points are far away. Other examples, there's this thing called the Mahalanobis distance. It's also a kind of one for real valued vectors. The nice thing about this one is that it's scale invariant, so you don't have to normalize your data before you use it. And it also, to some extent, takes correlation into account. So if you think you have got highly correlated variables, that's kind of already, it removes the effect of the correlation when you calculate the distance. So this this matrix equation here for vectors x and y is how you would define this distance. Another distance function that you might see is Hamming distance. So this can be used to compare maybe two different sequences of the same length. So it could be genetic sequences or any other kind of sequential data that you want to compare. And what the Hamming distance does is it just counts the differences at each point in the sequence. So they both start with a G, so that's not different. The next one is an G here and an A there, so that's one difference. That's the same, and that's different. So we have two differences. So the distance there between these two strings is 2. And that's used, for example, in some biological applications for matching short genetic sequences. So depending on what you're trying to compare, whether it's a sequence or whether it's a bag of words or whether it's an image or whether it's a numbers in a table, you can pick different distance functions. But you then plug it in and you can still do this same k nearest neighbors algorithm for classifying your point. You just need to be able to calculate the distance. One final distance you sometimes see is this Manhattan distance. Instead of doing the diagonal as the crow flies distance between 2 points, it imagines a kind of multi-dimensional Manhattan. You have to go around the block to get from this point to this point. You can't go through the building. So you just sum up the distances in each direction to come up with the total distance. That's sometimes more relevant. So that's choosing the distance metrics. And again, that normally boils down to the kind of things that you're trying to compare. The other thing is how we choose the value of k in this case. So what we can do here is divide our data set. So we choose our similarity or distance metrics. Yeah. There was a question about principal component analysis to reduce correlation. Does this find its way into machine learning? Yes, indeed. Some people consider PCA, principal component analysis, to be a form of unsupervised learning. It is a kind of step that you can take. Often you don't need to. Often you can just throw all of the data straight into your machine learning algorithm without doing a sort of principal component analysis first. Reasons that you might want to do PCA first is to reduce the computation time of your model fitting, for example. because it just sort of reduces the calculation instead. So instead of having many features, you can do PCA first and reduce it to a smaller number of features and then do the machine learning. So it can be a bit of a trade-off between speed and accuracy, because ultimately PCA is throwing away information. You're doing it in an intelligent way to throw away as little information as possible, because you're throwing away the stuff that doesn't really matter because it's not a principal component, but it is ultimately throwing away information that could potentially have some predictive power. So it can be used and is used in machine learning, but it doesn't always have to be used. So how do you choose K? Well, often this is about trial and error. Remember, we're ultimately trying to classify our data as best as possible. So what we can do is take our existing data that we already have and split it into a training set and a test. For example, 80-20. Next, we choose an evaluation metric. Now, remember I said earlier on, there's different definitions of what makes a fit good, what makes a model good. In this case, you might choose accuracy as the fraction of correctly classified instances. That's probably a reasonable one to use. And then what you would do would be to run your algorithm multiple times with different values of your hyperparameter, here K, using the training set to build the model, and then you evaluate your accuracy using the test set. So your test set is not used in training, it's used to see how well, at least on that test set, the classifier performs. So in this case, then you would choose your K to be the one that maximizes the accuracy. Now, of course, you don't know that that necessarily will maximize K, that maximize the accuracy in the real world on your unseen data. But given what you've known, what you've got from your training data that you've split into your training set and test set, that's going to be your best guess at what the best accuracy will be obtained with. So here's one example of a problem where you would run it multiple times with different values of K. And in this case, it looks like the peak is, well, it looks like you don't need very high values of K, which is actually quite common. Maybe here the peak came at about 18 or something as the best value. This is quite a typical shape as well. It'll drop off considerably as K approaches the number of points you have in your set, because at that point you're just kind of looking at everything. You're looking too far away. You're not really learning about what points are next to each other. So you typically want a value of K that gets rid of the noise. It gets rid of the chance that you're using sort of unreliable, a small number of neighbors that may not be reliable. So you want to average over as many possible, but if you pick too many, you lose the idea of which ones are close. So you could run something like that and pick a value of K. It's not easy to pick hyperparameters in general, but that is one approach that can be used. It's picked out K equals 4 as the best. I went for one of these pair, but I think it's chosen K equals 4. Okay. In this case, the model, the training set only had 75 instances, which is why the accuracy falls right off as you approach that. This is maybe a little bit out of place here, but just a comment on the performance of this algorithm. So one thing about K nearest neighbors is that there are various possible ways you can parallelize it. and scale it up. If the evaluation set is small and the model set is large, you can parallelize on the model set. Those are the training set. If the test set is large, maybe you could parallelize on the test set. You could parallelize over different candidate K values, for example. For those of you who know what MapReduce is, you can distribute the model set and then do a map function which takes the model instance to a key, which is the distance, and the value, which is a category. Probably most of you won't be familiar with MapReduce, but it can. So here's an example of how MapReduce can be applied in this case to do this kind of thing at scale. It also, so one thing that we come on to right at the end of the course as well, is we use a framework called PyTorch to do some machine learning. One of the advantages of using a framework like PyTorch is that with a couple of lines of code, you can switch from using CPU to doing your calculations on a GPU, which can massively improve the performance of the training in some cases. Why are GPUs good for this kind of thing? Again, it's because it's mostly matrix algebra. You're doing a lot of matrix multiplications, and this is the kind of thing GPUs are generally quite good at. In this case, this kind of algorithm does map well onto a GPU as long as you choose non-branching distance functions. Okay, so in summary then, for k-nearest neighbors, how are we doing for time? I meant to be finished classification by when? .3 okay, still got a little longer, good. Yeah, so k-nearest neighbors in summary, it's a way of doing classification. The output is a class. It's a supervised learning model because we have the training data. We have the red and green points as our initial data. The features for k-nearest neighbors don't need to be numeric. We've seen examples of words and things, as long as you can calculate some kind of numerical distance measure. In this case, it is a slightly unusual supervised learning model because, unlike something like linear regression, where we can replace all the dots with the straight line, what we effectively do with k-nearest neighbors is keep all of the training data and use it as the model. So the model in this case is the full training data set, which means that it is quite large and slow to apply. That won't be the case for most classification models. In terms of learning here, we need to either choose or to learn, evaluate the best possible value of the hyperparameter k, and depending on the distance metric chosen, and in most cases, you will need to do some kind of normalization. That's a one-off, a one-time transformation of the data so that it has a similar scale and spread in all directions. So a few words now about evaluating a classifier. So we'll talk a little bit more about the training and test set that I mentioned before. So the first thing to say is that it's bad practice to evaluate your model on the same data that you use to train it. So what you should do, and what is done normally in machine learning, is to split the training data, the data into a training set and a test set. In fact, you can even go beyond this and have a training set, a validation set, and a test set, where you can use that to sort of choose different hyperparameters or choose between models. I'm not going to go into the details of that here, so we'll just stick with the training set and the test set just now. The idea of the validation set is very similar. It's just that you do things in 3 stages rather than 2. So using 20 to 25% of the data as a test set is quite common. It's often a sensible default. So you train with the training set, and then you decide how good your fit is, your model is with the test set. When you run your model on your training data, you will get something called a confusion matrix. Yeah, Stephanie had a question.
Just a question, how to select the training set and the test set. Would you just randomly apply 20% as a test set, or is there a selection process?
That's a very good point. I don't know if I come onto that or not, but I can answer it now anyway, because it makes sense. Choosing at random is normally a good way of doing it, because if you have an ordered set, somehow, even if you're not aware of the ordering of the set, maybe choosing the last part of your data set as the test set can give you something that's not representative of the set as a whole. You know, if there is an underlying order to the data in your data set, picking all the measurements at the end might give you only recent data, for example, or something if they're time based. So picking at random rather than picking instances off the end of your set is normally a good way to do it. The only reason not to do it at random is that particularly if you've got if you've got class imbalance in your data. So if your training data has very few examples of one particular class, for example, you might want to make sure that both your training set and test set have a similar proportion of that particular class, for example. Otherwise, if a rare class is completely missed out of the test set, then you'll never know how good your model is for that particular rare class. So generally speaking, random is good. Random is the best approach. Sometimes you might want to impose some other constraints to make sure you've got some kind of class balance or making sure basically that the training set and the test set are drawn from the same distribution. Normally, random is a very good way of doing that, because if you're picking at random, you should get, in the limit of large samples from large populations, that you're going to get representative sets by doing that, by picking at random.
Thank you.
So once you've run your model, so you build your model and then you run it on all of the data in the test set. And so you train it with the training set, and now you've got a model. You don't touch the model again, you just put the instances from the test set into your model and you get a prediction. But of course, your test set also has labels. So you know the real values that it should come out on your test set. Here it's labeled gold standard. But you also make a prediction with the model that you've created, and that's the test outcome. So in this case, we have all of the ones that should have come out A. Most of them were correctly predicted as A. Some of the A's were misclassified as B's, and a small number were misclassified as C's. Here, of the ones that were really a B, 70 were misclassified as A's. Most of them were correctly classified as B's, and again, you've got a small number here. So ideally, what you want would be big numbers on the diagonal and small numbers everywhere else. Ideally, zeros everywhere else. It gives you would give you a completely accurate model, a test accuracy of 100% if everything was on the main diagonal here in the confusion matrix. So the confusion matrix is maybe tells you a bit more than just a single accuracy number, because you can also look at, well, are some particular classes hard in some way to classify, or are some predicted answers much more common than others? So a confusion matrix is often a good way of giving a quick impression of how good your classification is. So accuracy, if you just want to boil this down to a single number, accuracy is the fraction of correctly classified cases. So it's the fraction yeah, you would just, it's this number plus this number plus this number divided by every possible number here. The sum of all of the numbers here would just give us the accuracy. You can, one thing you can do is very similar to accuracy, but you can also do some weighted measure. To go back to the poison mushroom example, I might want to be much more sure about my poison mushrooms than my non-poisonous mushrooms. So you can apply different weights to different features if some of them are more important to you in some way. The binary version of the confusion matrix is, well, you would just get a 2x2 confusion matrix, where this number is sometimes called the true positive, the number of true positives. This is the number of false positives. This is the number of false negatives, and this is the number of true negatives. And then from those numbers here, you can calculate a variety of different things. So the accuracy that we've already talked about. There's another thing called sensitivity, sometimes called the recall or the true positive rate. And that's calculated like this. So what that does, it's some kind of measure of those that are positive, how many do you find? So that could be very useful for our mushrooms. Of those that are poisonous, how sensitive is our test at finding the poisonous ones? Now, of course, you could always just predict everything as being poisonous, in which case you never eat anything, but it's a bit of a useless algorithm. So you can, depending on the kind of classifier, you can change, you can often look at, you can change sort of trade-off between these different things. So sensitivity is like a measure of how well it finds the positive ones. Specificity is a measure of how well it ignores the negative ones. You can also do precision, negative, predictive value, and so on. Another one that you'll see quite commonly is this thing called an F-score. In this case, it's just calculated from some of these other numbers up here. It's 2 times the precision times the recall divided by the sum of the precision and recall. It is a kind of balance between sensitivity and specificity. In some contexts, this can be quite useful, but it really does depend on the kind of question that you're trying to answer. Another thing that people sometimes look at in terms of defining what makes a good prediction overall is to plot something called the receiver operating characteristic curve, or the ROC curve. This is just a plot of sensitivity against specificity. So, and often you can choose say a threshold for choosing a value as being a particular a positive value, and that corresponds to choosing a point on this curve. So you can always, with many algorithms, get a trade-off between specificity and sensitivity. If you have a curve that is close to the top left-hand corner here, it's good, because that means it's a good in terms of sensitivity and good in terms of specificity. So ideally, you want your model to produce a line that is towards the top left-hand corner of this graph, if possible. So I think, I can't remember if the practical covers some of this or not, but what you can do is, normally to get this curve, or sometimes the whole curve is reduced to another single number, which is meant to characterize how good your model is. And then the number being close to 1 is good, and close to 0 is bad. It measures the area under this curve. So if you have a curve again that's close to this corner, nearly all of the area is under the curve, so you get an area of 1. If you had a curve like this, close to this corner, the area under the curve is close to 0 because you haven't got much space underneath it. So you'll see these values quoted as well when people are talking about how good their models are, the area under the curve. Okay, so I think that covers what I want to say on classification. So the key point here is that there are, first of all, the algorithms have hyperparameters in them again, which can be quite hard to find. Next, you've got the idea of the training set and the test set. And finally, you've got this idea of there being different ways to evaluate your classifier, so that you can decide what you consider to be a good model, what you consider to be a bad model. Okay, so 5 to 3, not bad. So now we've got a short practical on k-nearest neighbors classification. So you can give that one a shot. And then at 3:15, I'll take a short break again. So, like with linear, the start of the last practical and with this one, we're using a library called scikit-learn, which is common, it's widely used. It's very good because it's got lots of built-in machine learning algorithms, right up to the point that it includes a basic neural network algorithm. Once you move on to more real-life neural networks and deep learning, there are other frameworks like PyTorch and TensorFlow that are widely used for doing those kind of things. But for a lot of the machine learning algorithms, scikit-learn is very good and very useful. So that's what we're using in these practicals. They should be online indefinitely, Omar. Archer tries to keep all of its material available online in the Git repository. It should remain live for the foreseeable future. Good question. I will have to ask my colleague. I'll just do that now. So sklearn is widely used for some basic machine learning. Yes, it is widely used. These days, neural networks are taking over so much that many people are moving towards using things like PyTorch and TensorFlow in real applications. These are much more computationally intensive, though. So there's often a good argument to start with the kind of algorithms that you've got in scikit-learn. See if they are good enough for the kind of problem that you are trying to address. If you can't, and you need to use deep learning or so on, then by all means move up and move on to something like PyTorch or TensorFlow. But the scikit-learn ones are widely used in production and are generally more computationally efficient, or not necessarily efficient, use less computational power than trying to run massive neural network models.
If I use the train, test, and split method, and I assume this goes by randomly selecting data to put into the test and into the train section. Now, if we say we have one of those not biased set, but more of the sets where one category was a lot higher than the other, would there be an option with train, test, and split to specify that?
I don't think so. I think you'd have to do it manually.
Okay.
Yeah, train, test, split is a sort of convenience function to do the random splitting of the data, but
yeah,
you could do it manually if you prefer. I'm just trying to see. So one thing that you can do to find a bit of documentation on all of the functions is to so I'm going from sklearn import train, test, split first of all, and then you can. Okay, I got that wrong. To get more documentation on anything in Jupyter Notebooks, you can just start with a question mark. So if I wanted to find out what train, test, split could do, I can type question mark train, test, split, and it tells me that, so these are the options. It gives me, you can either specify the test size or the training size. You can pass in the random state. So if you're trying to do this in a reproducible way with a random seed, which is stored in some object, which is the random state, you can do that to keep track of that and do it in a reproducible way. Just pass an integer for reproducible output across multiple function calls. By default, it does a random shuffle of the data before splitting. So there is something called stratification. So it can do something in terms of preparing the data. It says look in the user guide under stratification. Folds are made by preserving the percentage of samples for each class. Yeah, so it can do some, so it has got some functionality for dealing with class balance. It's not something I've ever actually used personally, but it looks like there is something there that could help with that. So you might not have to do it all manually.
Thank you.
Omar, to answer your question about how long the training accounts stay open, the training accounts stay open for 1 month on ARCHER2. I should say, if you're looking at these practical sessions after the training course, and you have any questions, you're welcome to email me. I think my email address is on some of the slides. I can't always promise that I will respond quickly, depending on what other work I've got on at the time. But I will try to get back to you with with answers to any queries that you have. So if you're following up later and you're stuck on something or you have a question, I'm happy for you to ask me by email. So I think the practical says at one point, from the output above, you should be able to see what value of k is chosen by default. It looks like the output that was given by classifier.fit has changed since the sheet was written. And it now seems to just produce this blue box, rather opaque. The kind of information that I think it used to produce, you can get with a call to get params on the classifier object. So you can see that by default, you can see that it's done k nearest neighbors. So the metric here is the distance metric. It's using Minkowski, which is another name for a Euclidean distance metric that we talked about. And we can also see that it's using k equals 5 by default. It's using 5 nearest neighbors and uniform weights. Okay, I make that 3:30, so I'm going to make a start again now. To give one more talk today. I've got 50 minutes set aside. I don't think I'll actually need that. But we're going to now talk about an example of an unsupervised learning algorithm, a clustering algorithm. So to see where this fits in again, so now we're going down the unsupervised learning branch. So they're looking for patterns in data, and we're going to do see an example of clustering. Most of what I'll talk about is k-means. I will actually touch a little bit on distribution-based clustering and density-based clustering, just to give you some other examples. But most of what follows is k-means as an algorithm. Confusingly got a k in the name. This has got nothing to do with k nearest neighbors that we've just looked at. It's just another hyperparameter. It's a completely different kind of algorithm. But it just so happens also to start with a k, which can be confusing sometimes. So the idea behind clustering is as follows. So if we as humans look at something like this on the left, we can probably see that this data, well, sort of falls into 3 groups, 3 clusters. We can visualize that quite easily, at least in 2 dimensions, when this data has 2 different features. It gets much harder when you go up to data with more features to work out which ones are similar just by eyeballing the data. That said, eyeballing is still a good thing to do as part of your exploratory data analysis before you try to do any predictive modeling or anything like that. And clustering is often done more as an exploratory step, maybe before prediction, but it can be used as an algorithm in its own right, as I've given examples, to sort of segment your customer base or split whatever things that you have your data on into groups. So yeah, visually we can see that we want probably all these points to be given black, these ones to be labeled red, these ones to be labeled green, so that we've got 3 different groups, 3 different clusters. So we're assigning a cluster number to each point. We're assigning a color, in this case, to each point. Of course, that cluster number, what does it mean? It doesn't mean anything. It's not like in supervised learning where you've got some feature that you're trying to predict a value of something in particular. All you're saying is that every other point that I paint that color is similar in some respect. It's got similar features. So you're assigning a label, but it's not a label of a particular category or class. You're not doing classification. You're just giving it a cluster label. So it's equally valid. This one could be green, this one could be red. The order of the numbering that's given to a cluster is completely irrelevant. So how would a computer do this? How, given these points, would a machine decide which points to put into the same cluster? Well, there's different kind of approaches, but we'll start with the example of k-means. I've got a couple of slides on notation here again, just so that I can use some mathematical shorthand. I think this should look pretty similar to the notation we had before. Yeah, so here we'll use the superscript notation, I think, is the one that matched what we had before, where the index represented the I can't remember which way around we had it now, actually. Anyway, I'll try and make it clear as we go through. I should double check that all of this is consistent. So again, I'll point out what I mean as I go through. So k-means clustering, first thing we have to decide is that we have to know in advance how many clusters that we want to group the data into. We might not know that. So there are ways, again, of working out, or of trying to find the best value of that hyperparameter k. Some algorithms don't have to specify in advance how many clusters that you want to look for, but they may have other hyperparameters instead. So sometimes it's easier to choose the number of clusters. Sometimes it's easier to use a different algorithm. So with k-means clustering, given these observation vectors, so m different observations, m different points on the plot, can we group them into k distinct sets? So give them k different colors. So in our previous example, m was fairly big. We had quite a lot of dots on the plot, and k was 3 because we were trying to plot them into 3 different groups. We are trying to minimize the within cluster sum of squares. So what we're trying to do is, given the points, we're trying to arrange them such that for each cluster here will have some sort of central point, some mean value, which we have to work out. And it obviously depends on what all the points are. So we're trying to minimize the total distance of points from a central value. So we're trying to come up with some points, some central values, such that we can have as little distance as possible from each point to the centroid mu. So here mu c is the mean of all the points in the set SC. So we've got the same number of centroids as we have colors. The color goes from 1 to k because we've got 3 different clusters, and we're taking all the points in the set and we're trying to minimize the distance, the total distance of those points from the centroid. just like before, so what we have here, I'm using the double bar notation to show a distance. Again, remember this kind of algorithm can be used for all different kinds of data, as long as we can define that distance metric. So as long as you can define the distance between 2 points, or between a point and an average point, then you can use this algorithm. So although it looks like we're using numbers here, real values, these could also be images or sounds or document sets of words. So the algorithm is as follows. We define each cluster by the centroid of the values in the cluster. We start by choosing k random centroids. These could be some of the observations, or we could just pick them in some other way. And then we repeatedly assign each observation to the nearest centroid and update the centroids to be the mean for those observations assigned to it until there is no or very little change in the centroid. So I'll show an example of this in a moment. But it's a repetitive, an iterative algorithm, unlike the k nearest neighbors, where we just have to look at the closest points. In this case, we have to repeatedly sort of move the centroids, reclassify relabel the points in the cluster, and then measure the distance again, and we keep adjusting it until there's little or no change in the centroids. So I'm about to do a video, and unfortunately this video runs a little bit quickly, but I'll let it run, and then I'll explain what's going on. So before I start it, here the centroids have initially been chosen at random to be here, here, and here. So as this loops, so we can see that the first thing that it does is it moves this x to, so this x here represented all of the black points. So it moves it to the middle of the black points. Similarly, the red one was moved to the middle of the reds, the middle of the greens. And then once it's moved, it reassigns all the points again to the nearest one. So you kind of assign observations, then move the centroids, and repeatedly go backwards and forwards. In this case as well, we have to normalize the features, just like we talked about before, so that they have the same scale and spread, so that you're not biased towards a particular feature. We need to think carefully about those features that you want to include, as what this algorithm just gives each feature equal weight. It can be hard to interpret. So it's not always obvious once you've done a clustering what the clusters represent. So sometimes the clusters seem meaningless. If this has been done in a kind of data mining-y type scenario, this is where it's quite useful to have things like some domain knowledge. So once the algorithm has come up with clusters, it can be quite useful for a domain expert, somebody from the business or whatever, to look at the results and say, I think I know what those clusters might represent. These ones are grouped over here because, I don't know, these were on our old plan before we changed the deals that we offer to our customers or something, and they're still on the old plan that you can't sign up to anymore. These ones are on something else. So sometimes somebody can look at them and they can assign meaning to the clusters, but it's not always easy to see what the actual meaning of being in a particular cluster is. You need to choose your value of k. Sometimes you know that there are K processes generating the data. So again, you might have some idea of roughly why there might be different number of clusters. Again, if you have some domain knowledge. Sometimes it's just by trial and error. And another thing that you can do is to plot the cost that you calculate. So the cost here is like the cost function that we talked about in linear regression, for example. In this case, the cost function is the within cluster sum of squares, because this is what we're trying to minimize. So if you plot that cost against K on a plot by choosing different values of K, you'll often see a knee, a place where there's the sharpest angle in the plot. I don't know if I've got an example of that. I probably should find one. But that shows you a good value of K to choose. It's a kind of good trade-off between getting, by not having too many clusters, but having them mean something. But having them suitably, the word I can't remember, differentiate between the two different groups. So this algorithm has some limitations. The clusters are assumed to be of the same size, i.e., yeah. So if you had an example like this, for example, I think a human looking at this would probably say, okay, we have one big cluster and two little clusters up there. But what k-means would do would be come up with something like this. So it would sort of have the same three clusters. It would still find roughly where the cluster centers were, but it would misassign points because it assumes the clusters are of the same size. And clusters on density are not so good. So in this case, probably a human looking at this would say, right, we have two clusters here. They're kind of overlapping in some strange way. But we can see that we would probably want to give all of these ones the same label, and also give. I don't know, you can't see my mouse pointer, can you? I thought you could see them. Anyway, all the top ones the same label, and all the bottom ones the same label. Yeah, these ones and these ones. Was that a question? Oh yeah, you can see the mouse pointer. Okay, I was looking at the wrong screen. Yeah. Okay. Oh, that's really bad. I've broken it now. Turn that off again. Just give me my slide back. Yeah, so if you're trying to cluster on density, what k-means will do is come up with something like this, because it just tries to group nearby points together. It doesn't look at actually the relative density in different points of space. So that's one sort of simple example of a clustering technique. There are other techniques called distribution-based clustering, and what they do is allow you to kind of give a suggestion to the model that, okay, I'm expecting my points to fall into some distribution, but I'm letting you decide the parameters of that distribution. In the same way that we sort of said, okay, it's a straight line, but you can decide where the straight line goes. In this case, we're saying where I'm imagining my points will be sort of uniformly distributed in each direction, and you can also change the size of the cluster to accommodate it. So in these distribution-based clustering models, they take a little bit more time to run than something like k-means, but they're the same, roughly the same principle, but they allow it to model clusters that are of different sizes. So distribution-based clustering then handles covariance of features. Generally speaking, there's no need to normalize data. This is a comparison, for example, what a distribution-based clustering algorithm might do compared to k-means again. It's still not very good at these kind of scenarios for density-based clusters that don't match a distribution model, because it still tries to fit some kind of distribution to these to the points that it finds. So better than often better than basic k-means, but still can't handle all the scenarios. I've got I think these slides may not be on the repository, but I'll add them afterwards. Just the last few slides on clustering. The final one I was going to give you an example of is density-based clustering. And in these algorithms, you look for clusters that are of higher density than the rest of the data set. The classic example of this one is called dbScan. And this groups together points which have many nearby neighbors. Points with few nearby neighbors are marked as outliers. In this case, one of the problems with density-based clustering is that it's got two parameters that you have to set, two hyperparameters, that should say hyperparameters. And these can be quite hard to work out what the right value should be. It's a bit of trial and error. You need to specify an epsilon, that's the distance below which points are considered to be neighbors, and also this other hyperparameter minimum points, which is the minimum number of points required to be considered a cluster. So you have to provide both of those. The algorithm here is again in practice, I don't think I've got it written out here, but this is again the way you actually implement this algorithm is fairly iterative. So all points are either identified as a core point or a density reachable point or an outlier. And then the cluster is defined as containing all of the points that are mutually density connected, and also contains points that are density reachable for a point in the cluster. It gets a little bit mathematical. You don't really need, I don't think it's hard in a short course like this to sort of explain in detail what's going on here. But the end result is the most important thing, is that it can identify these kind of clusters here. So it can find the two different clusters, which are the same ones that probably our eyes would pick out. As I said, unfortunately, it can be quite hard to find the right values of these hyperparameters. If you set epsilon too low, in this case, the result is it thinks that there's another little cluster here on the end. If you set epsilon too high, it just assumes that these are part of the same cluster. Is the middle the correct solution? So that raises a good point, right? So the word correct there. Clustering doesn't have a correct solution. In our case, we made some artificial data, and okay, they did belong to two different sets. But really with clustering, there is no right or wrong. It's whether the clusters mean something to you. There are ways to define, there are metrics that people use. You can compare the within cluster sum of squares to the between cluster sum of squares and do things like that, and try to maximize between cluster sum of squares and minimize within cluster sum of squares. So there are metrics that can be used to define good. But unlike classification, where you have labeled data that you're trying to match with a test set, there isn't really right or wrong. What we are looking for are points that have something in common. So normally with clustering, the proof is in the pudding. You run it and see if the result is meaningful to you. In this case, probably the middle one matches our expectations of what we would like to get out of the algorithm. Again, this is a simple case. We can see 2 dimensions. It's obvious to eyeball it. In a much higher dimension, it might not be so immediately obvious which one of these is better, which is when you might fall back to using the metrics, like trying to have within cluster sum of squares to be small and between cluster sum of squares to be large. Then what that is saying is that you have points that are definitely are in 2 different groups or more different groups. But yeah, there is strictly speaking no correct solution to clustering. All it does is group the points together according to the algorithm. There's not really an underlying truth. So I don't think I've got any more slides. I was just going to finish off by showing you again the scikit-learn before we get into the final practical. The documentation in scikit-learn, unsupervised learning, clustering. So this is quite a nice summary. So we talked about k-means. It's called mini batch k-means here, but that's basically the algorithm that that I showed you with the moving the centroids. And we've got the 2 other ones that I talked about were I think the distribution based was a Gaussian mixture model, because it was explaining though that we were saying that the distributions were basically, they look like ovals on our 2-dimensional plot, but actually in 3 dimensions the distribution, the shape of it is Gaussian in different directions. If you can imagine that as a 3-dimensional shape, or so yeah, that was the Gaussian mixture model, and dbScan is the one that we looked at that managed to separate out these 2. So this gives an overview of these different kinds of data sets. What do the different algorithms do? And you can see that some of them work better for finding the density-based ones are better for shapes like this with rings and overlaps. Gaussian mixture is fine for ones that maybe spread out in a particular direction, whereas k-means doesn't work quite so well for that. You can also see, I think these numbers in the corner are a runtime of how long things took. It's a bit hard to compare here, given they should multiply each of these by 10, I think. Or for this data set, maybe it's just so small that they run so quickly anyway that the performance is not important. But that's the other thing that you would normally take into account in practice when you're choosing between different clustering algorithms, is A, how well do they perform on the kind of data that you have, and B, how long do they take to run. So yeah, as again, quite a few different examples there in scikit-learn. Is there a score how good an algorithm works? The closest thing is so if I look at this section, clustering performance evaluation. So in particular, any evaluation metric should not take the absolute values of the cluster labels into account, but looks at the separations of the data. So you can calculate various metrics like this RAND score, which looks at I suppose, at how good the clustering is. The other classic one is to compare the two different sums of squares. I think the practical, does the practical maybe have it does give a score. So if I do k-means, I think one of the things that you can get out of it is, I think it's just called score, is it? Yeah, it's got an awful definition. Opposite of the value of x on the k-means objective. It's like kind of the opposite of the cost function that's calculated. So you can get some kind of metric which is a score, which does compare, at least for similar algorithms or the same algorithm with different data sets or different distance. Well, no, it has to be the same distance metric. You can compare scores, which are similar to like the total within cluster sum of squares. I'm talking about within cluster sum of squares and between cluster sum of squares, just to give one other sort of, what do I mean by that? Here, I'm looking at all the points within a particular cluster and adding up the distance of those points from their mean. That is, adding up all the points and distance from their mean is kind of equivalent to adding up the distance of every point from every point to every point in the same cluster, and add that up. So number 1 to number 2, number 1 to number 3, number 1 to number 4, number 1 to number 5, number 2 to number 3, number 2 to number 4, number 2 to number 5, number 3 to number 4, 3 to 5, 4 to 5. Add up all the distances. That's the within cluster sum of squares. And if it's a closely defined cluster, you'd want that to be small, because that means that all the points that are in the same cluster end up close together in the space of features. Whereas you would want to minimize that, but you want to maximize the distance of points in other clusters. So the between cluster sum of squares is that you take every point in one cluster and every point in a different cluster and measure that distance and add it all up. So you're trying to find points that are close to each other. You want all the points that end up in the same cluster to be close to each other, and all the points that end up in different clusters to be far away from each other. And so the ratio of those two numbers within cluster sum of squares and between cluster sum of squares is probably the most general metric of that you can use to compare two clusterings. But it is not really a good way of comparing, not completely general. I mean, if that works, that often does work to compare two different algorithms, but it doesn't always work. So you have to just see if the result that you get is meaningful. Gudrun, you want to ask a question to follow up? I can't hear you. I don't know if you're trying to speak. I'm not hearing you at the moment. Okay, so maybe I've answered your question already. I'm not sure. Either feel free to open your microphone or to type into the chat again. It's a difficult one to answer. The closest thing you've got here is this score. And more generally, I think that ratio of between sum of squares and within sum of squares is probably the best general metric to try.
Hi, so I can speak now, I think, right?
Yep. Mm-hmm.
So, could we go back to that overview with all those clustering methods, please?
Mm-hmm.
Yeah, sorry, I think my PC is very old and slow. Yes, so when we look here, for example, to the column of spectral clustering, yes?
Yeah.
Then the first two data sets are equally well described by this algorithm, and maybe below as well. So then, but also like,
that looks pretty good.
Sorry, but then we can also see. Nee, so that was my mistake. Yeah, okay, nee, then it's fine. So then, sorry, I mistaken this. Yeah, my fault. Now I can see that this is probably the best classification for this kind of data set, the spectral clustering. And I got confused with the one below. But it tells me also, on the other hand, that this one algorithm I can obviously use for various kinds of clusters, and it seems to perform equally well, maybe. I mean, depending. Okay,
it does seem to be pretty good. It seems a bit. The only thing that it falls down on is that it seems to be a bit slower.
Yes, but
than
then
the other ones. But,
maybe I can afford this with my cluster. So
yeah.
Okay. Yeah. Okay. Then, sorry about the interruption.
Mm-hmm. No, it's on the face of things, the spectral clustering does look very good there, and I think it is considered to be a pretty good clustering technique. The implementation is maybe a little more complicated, but that doesn't really matter if you're calling it from scikit-learn.
But when you look then for about DB scan, HDB scan, and optics, then it comes down only to the time, how much I want to invest.
Yeah, these DB scan and HDB scan, they're very similar implementations actually. They seem to, DB scan and HDB scan seem to be doing something a little bit different with the outliers. Okay. But the other thing is, of course, the choice of hyperparameters that you have to get in.
Yes, and that is maybe another question when we in this other slide where you showed us the three clusters. You said it was difficult to find those hyperparameters, right?
Mm-hmm.
Do people run a search on those best hyperparameters, and how would it work?
It's quite common to do that, yes, to have a kind of iterative empirical approach to this, rather than to try to choose the best hyperparameters in advance a priori. They run it multiple times and see what gives the best one. That's quite common in practice.
But I heard that hyperparameter tuning is very costly.
It is.
Okay, I will explore a bit more.
Well, it depends. I mean, if you're trying to do it on these kind of models, particularly some of the things in scikit-learn, you'll see from even fairly big data sets, these algorithms are fairly fast, so that it's not too computationally difficult to try different values of hyperparameters. Once you start getting onto deep neural networks, which are computationally more costly, the hyperparameter tuning does become, it can become prohibitively expensive. It's a bit harder to do it certainly you can't kind of just explore the whole space of possible values. You have to be a little bit more selective about the ones that you try.
Thank you.
Okay, so there's one last practical on k-means clustering that you can have a go at today. In fact, there's two versions of this. There's one that's really quite short, which probably covers everything that most of you would want to know. This, some of you were asking some quite, well, deeper questions about what makes good clustering and the metrics used. The longer version of this practical, I think I can show you at least the notebook inside GitLab here. It goes into more detail about the hyperparameters and how to compare them. So this, yeah, I think for most people, I would recommend just doing the shorter part, the shorter version of this practical. But if you want to get in more depth and explore the hyperparameters a bit and so on, the long version also does shows you the an implementation written by hand, which helps you understand what's going on inside the implementation. The shorter version really just covers using the library from scikit-learn. So have a shot at whichever one you want, either the quick one to just see how you would call it from scikit-learn, or you can dive a bit deeper into the long one if you want to actually look at what's going on under the hood. Yeah, and I should also point out that there's nothing in the longer version that's required for understanding the things on the about the machine learning, for example. It just goes more into in depth on clustering algorithms. Struggling to find any value of epsilon that works for density-based classification in this case. If anything, that illustrates the difficulty of choosing hyperparameters, but I wouldn't worry about it if you can't find a value of epsilon that works.
Hey, Adam.
Mm-hmm.
Do you reckon everything's being labeled noisy because your data's quite sparse, and so that minimum number of points being 5 initially, none of the points are really that dense, and so it's kind of difficult for even I guess if your epsilon value was massive, then that wouldn't matter. But if you just reduce the number of points that are required to be in a cluster.
Yeah. So you're right. The starting point for, maybe if I reduce that.
It's nice to be right.
There we go. Oops. That was, I don't know why. It's nice to be right came from Siri, who seemed to jump into my conversation here. So you are right though that this that reducing the minimum samples allowed it to find some initial points, and now if we increase epsilon, it should find points that are yes, better. Yeah, so you were right. Because the data was fairly sparse, and it looked like because of the choice of initial clusters that it picked, we're all in this. Maybe it's irrelevant that they were all close together, but yeah, the data was undense enough. Well, that's good. You have more more feeling for the hyperparameters in dbScan than I do. But yeah, so that you're exactly right. So by decreasing minimum samples there and then increasing epsilon, we've managed to find some clusters, although we've still got some outliers here. But
so the only reason why I'm seeing that is because it's easy to visualize the data, right? But that's very unlikely to happen in real life. Like the data I work with has like hundreds of thousands in dimension, right? So this doesn't feel like the most useful machine learning algorithm that we've gone over.
No, yeah, I think it's a particularly specific one, isn't it, for handling these strange cases where you've got somehow overlapping data that would fit with a distribution.
But in those scenarios, you kind of do it yourself anyway, right? And you're just like waiting for an algorithm to say the same thing as you are. It's like, where is the kind of middle ground here where the algorithm's actually useful and I can't just do it myself?
That's a good question. Yeah, they're just tools. Larger data sets, higher dimensional data, automated things. There's sort of human in the loop in this kind of analysis at the moment, but you could have imagined scenarios that every day you've got a new data set generated by something, and you're trying to split it off so that an automated process can do two different things to it. So it might just be that it can be automated, or it might be that in higher dimensions or something like that, it's harder to visualize.
Okay.
But yeah, I take your point. They're just different tools in the toolbox that can be used to look for patterns ultimately.
Yeah. I guess it'd be quite useful if like you already had some kind of like gold standard for something that you've done yourself, and as the data gets bigger, it's harder to visualize it yourself, so you can just have an algorithm go off and do that, and you kind of already know what it should be, but you're not learning from it, it's just automating that process of what you could do yourself if you had the time.
Yeah, so John was saying that automation seems potentially tricky given that at the very least some tuning of hyperparameters is required. I guess it would, that's true. I think it could only work then really if in the initial, if it turned out that maybe every time you gathered your data set, it tended to be similarly distributed or such that the same hyperparameters work, so that you could find them once and then reuse those values and hope that the characteristics of the data remain the same. But yeah, slightly risky. It could break down. Something I haven't really talked about, when I talk in more detail about data mining processes and things like automation, a good data mining process always includes a kind of continue to test your assumptions and continue to evaluate your output after deployment, or after you've put your model to use, because underlying assumptions can and do change. So that would help to pick it up if there was a change. So you would hope that it wouldn't change. You'd find your hyperparameters once, you'd set up the automation, and you would test some cases, repeat, on an ongoing basis to make sure that it was still giving you something that was meaningful. But yeah, the hyperparameter tuning and clustering in general, or the unsupervised algorithms in general, they are probably more use for exploratory data analysis than they are for predictive modeling and automation, where you just want something to run. So it's more about they are more just about really tools to look at your data from different angles and to spot different kinds of patterns. But yeah, I don't think I've got any real gems as to how to do hyperparameter tuning well in general. It's just a difficult thing to do. Okay, I do have to leave fairly promptly at 4:35 today, so if anyone's got any final questions, now is a good time. Otherwise, I'll pick them up again tomorrow. Yes, Yin?
So I noticed in the long practicals that there is a Python file with function for k-means. Does it mean that generally there isn't any library that we, so it use a Python file that you prepared early on, the my k-means.py?
Yeah. No, so it's not the fact that there isn't so there is an implementation of k-means as part of scikit-learn. The only reason that we've given you this version here is so that you can actually see. If you try to look at the source code of scikit-learn's k-means, it's quite complicated, and it's harder to actually see what's going on in the algorithm. This one is designed to be a little bit clearer, But it's here for you so that you can see how it is implemented if you want to go down to that level. But the alternative, in reality, if you're just running it, you don't care what the algorithm is doing under the hood, there is a perfectly good implementation in scikit-learn. Indeed, it's arguably a slightly better implementation. So as a good general point with all of these machine learning algorithms, the libraries and frameworks for these things are pretty good, and they've had a lot of eyes on them. And as a general principle with libraries and so on, it's better to use an existing library than to write your own thing from scratch. So I would recommend you using scikit-learn or something similar in practice. The my-k-means here is there as a sort of designed to be something that you can look at the code and see how the algorithm is implemented. Is that clear?
Yeah.
Yeah. So another thing you can do, see, when you write your own algorithm, you can dive in to actually look at some of these metrics, like the total within cluster, the total between sum of squares, the things that I was alluding to when I was talking about the best ways to evaluate the clusters. So although scikit-learn's clustering algorithms are very good, I don't think you do have, you've got access to that .score method, which gives you one of these, I think. But if you're actually trying to investigate different ways that you could measure how similar data is, you might need to go to your own implementation. Okay, I'm going to wrap it up for today and stop the recording. We will reconvene tomorrow morning at 9:30. So I hope to see most of you again tomorrow, and we can get onto the neural network part. Bye for now.